Right, we're looking at the 2010 Queensland Senior External Exam for Physics. This is paper 2 and it's question 5. First thing we do is we very carefully read the question. Speaker system has two speakers 1.60 meters apart on the same wall. During testing of the system using sound of frequency 640 Hz, the girl standing midway between the speakers and 8 meters from the wall notices when she moves to her left the intensity of the sound drops to almost zero. A. Explain this reduction in sound intensity using the principles of physics and determine the wavelength and the velocity of sound, or if the velocity of the sound was 320 meters per second. Find the shortest distance to the left that the girl must move in order for the sound to be at its lowest intensity. Right, we've read the question. Now we go through and we make sure that we identify all of the important information. Right, we have two speakers, 1.60 meters apart. There is a frequency of 640 Hz. The girl standing midway between the speakers and 8 meters from the wall, so she's 8 meters away. When she moves to her left, the intensity drops from zero. So when she moves to her left, the intensity drops to zero. When the intensity drops to zero, that means she's destructive interference, so the path difference from the two speakers must be a multiple of half a wavelength. Part A. Explain this reduction in sound intensity using the principles of physics and determine the wavelength. So after the wavelength, if the velocity is 320, now find the shortest to the distance to the left that the girl must move in order for the sound to be at its lowest intensity. Okay, for the sound to be at its lowest intensity. Alright, we've gone through and we've read and identified the information. Now we have a look at actually drawing a picture. Now, we have two speakers here on a wall. There's two speakers like so. Halfway between those two, there's a central line there, and we have a wall here, and the girl is moving backwards and forwards along this particular wall. So here's our girl. There she is, moving backwards and forwards along there. Let's go in and mark our particular distances. This separation here between the speakers, that distance D, is 1.6 meters. So it's the separation there of your speakers. During the test of the system, the frequency is 640 Hz. So frequency is 640 Hz. Very good. The girl is standing midway between the speakers and 8 meters from the wall. So this particular distance here is 8 meters. Now, that's our L distance. This is our D distance, like so. As she moves to her left, the intensity of the sound drops to almost zero. So there's our diagram. Explain the reduction in sound intensity. So to explain the sound intensity, for a start, the dotted line is equidistant and a perpendicular bisector between the speakers. So I'll label this the central maximum. Along the central maximum, the path difference to the speakers is zero. Therefore, constructive interference occurs. What we mean by constructive interference is a crest plus a crest equals a double crest. A trough plus a trough equals a double trough. So the central maxima, this is loud sound. Now, as the girl moves in any direction away from the central maxima, she will actually make her way towards what's called here the first minima. As the girl moves. Now, in what direction does she move? When she moves to her left, the intensity of the sound drops, so this will be to her left here. As she moves to her left, she approaches the first minima. Here at the first minima, the path difference to the speakers is lambda on 2. So this is destructive interference. Destructive interference. In other words, a crest and a trough add together to give you flat, or where we had here loud sound, this will be soft sound. So that's what happens as the girl moves from A to B. Now, can we determine the wavelength of the sound? Yes, we can determine the wavelength of the sound. There's a simple formula that we can plug these values into. Off our formula sheet, delta X equals L lambda on D. We can go through that, and we need to calculate the wavelength. The wavelength, transposing this particular equation to make the lambda the subject, multiplying both sides by D, the D's cancel out, and we get delta X times D on this side of the equation. If we divide both sides by L, the L's cancel out, and so therefore to work out our wavelength, it's delta XD on L, and so that's the formula that we need to decide to use. So let's lock in our values. Delta X is the separation This is the formula, of course, for the second part. To actually do this, I've got to be able to calculate the wavelength, and so the wavelength, the formula that we use to calculate that is V equals F lambda, and so we need to use V F times lambda. To calculate the wavelength lambda, it's V on F, and so that we know the velocity of the sound is 320, the frequency of the sound is 640, and so therefore we know that the wavelength here is 0.5 meters, but it's to three significant figures, 0.5 meters. So that's the wavelength. That's part A, sorry. And so let's put that wavelength into here. The wavelength is 0.500 meters. Now delta X is the spread. So let's put the values into this formula, sorry. L is 8 meters multiplied by the wavelength is 0.5. D is the separation of our speakers, which is 1.6. Now let's make sure that we've got all our measurements correct. The screen is 8 meters away. The wavelength is half a meter. Wavelength is half a meter, yes. And the speakers are 1.6 meters apart. So we can put those values straight into our calculator. 8 times 0.5 divided by 1.6 equals, therefore we get an answer of 2.5. Now 2.5 is the separation of the nodes, and so if we have a node here and we have a node here, the separation of the nodes is 2.5 meters. Now the girl is starting on the central maxima. How far does she need to move to get to that particular node? Given that this particular point where she starts is the center, so halfway between 2.5, it means she's got to travel 1.25 meters to get to the first node. So the shortest distance to the left the girl must move in order for the sound to be at its lowest intensity. The shortest distance is 1.25 meters, and that will take her from the central maxima to the first minima.